me to Article 450, I believe, and we're all the way. Here you go, 450. And in particular, table 450.3b. 450.3b, which is, you're looking at it right in here, 450.3a and 450.3b. And let's just talk a little bit about these. See if I can fit all of it in one shot here. Okay. All right. This, I want to bring you to your attention, guys. This table, there's table A and table B. If you have a transformer, and you need to size, here's my transformer, and I need to size the overcurrent protection device in the primary and the overcurrent protection device on the secondary of the transformer. The primary and the secondary overcurrent protection device of this transformer. If the voltage on the primary or the secondary of the transformer higher than 600, you use this table. If the primary or the secondary voltage, or both, higher than 600, you're going to use this table. If both of them are lower than 600, we're going to be using 450.3b. Okay, so when do we use this one? We use this one if both 600 volt, if it's higher than 600 volt, higher than 600 volt, primary or secondary. If the primary or the secondary or both higher than 600 volt, you come here. This one we're going to be using, guys, in the commercial project. So I just want to FYI it for you, and move on. We'll talk about this one more when we come to the commercial project. So I'm going to go to the one that relate to us, which is B. B, you use B if the voltage, you use B as it says, if both the primary and the secondary are 600 volt or less. Maximum rating or setting of overcurrent protection device for transformers, 600 volt and less. Both primary and secondary. That's where we are right now. We'll go to, as I said, A later on, but we'll talk about B now. Okay, so both primary and secondary. Here's a good example. Here's a transformer, nice, beautiful transformer with an overcurrent protection device right here. And this voltage is 480, and this voltage is 208 volt, right? Are both of them less than 600? Both of them less than 600? Yes, Chad, we can go ahead and use it. Let me snap a shot here at this. Any question, guys? What, less than 600? I'm going to go and just expand it a little bit. If you guys, gotta be a view. Okay, trying to get all of it in one here. Okay, that's good. If you guys look at you can have either primary protection or primary secondary protection. There's rules for primary protection only. Unless you know your transformer will have primary and secondary protection, unless you know otherwise. So we're going to go with a transformer that has primary and secondary protection. If the current is 9 amps or more, what's your multiplier, Brad? If a current 225. If your current is 250. If your current is more than 9 amps, which is 99% of the time, you're going to be dealing with amps more than 9 amps, right? Your multiplier is still 250, right? No change. This is on the primary side. On the secondary side, and there's also a current less than 2 amps, which is tiny little amps. This is for control transformers. If your transformer is less than 2 amps, your multiplier continues to be 250. If you go on the secondary side, guys, currents of 9 amps or more, that's most of the time you're going to be at 125%. I want to bring your attention to note number 1. Very important, note number 1. if you guys read note number 1 here, it says if your calculation end up with a non-standard overcurrent protection device, you have 3 options. Go to the bar, drink, and cry. Option number 1 doesn't say that though. Or custom design yourself a fuse that's 63.5 amp. Or option number 3 is go up. Can you guys see that? It says go up. In all these tables, Mr. Boo, unless it tells you to go up, you never go up on overcurrent protection device. Unless it tells you to go up. That's a rule. No going up on overcurrent protection device in any table in the code unless it tells you go up. Because going up is less protection. Going down is more protection. In circuit breakers. In conductors, guys, the opposite. The bigger the conductor, the more protection, or the more protected the conductor would be. The smaller the conductor, the less protected the conductor would be. Okay? The circuit breaker is completely the opposite. The bigger the circuit breaker, the less protection the equipment underneath it has. The smaller the circuit breaker, the more protection we have. Opposite of conductors. Okay, so, and on the other side, you guys can see it. It says if your conductors are small, which is 9 amps or less, what's your multiplier? 167. I don't think I'm missing anything on the other side. Okay. Any question, guys, about that? Mr. Erbab, do we know how to use the secondary side and the primary side? If I have protection on both sides of the equation, here's my fuse, and here's my second boy, here's my second fuse. That's protection on both sides of the equation, both sides of the transformer. Primary is going to be here, secondary is going to be here. This voltage here is going to be 600 or less. This will be 600 or less. So you can have any combo voltage. You can have 24 volt and 480 here, or 480 here and 24 here. Any combination, or 240, 208, any combo. Any question, my friends, about this table? I want to bring your attention, as I said, to this particular one. I also want to bring your attention to note number 3, which you see a lot. Note number 3. This is mostly for journeymen who's sitting for master. They always catch on that. Note number 3, guys. If you have a transformer equipped with a coordinated thermal overload protection, bigger transformers, certain transformers, they have an overcurrent protection device to protect them, overload protection. If you have this type of transformer, which you assume you don't have unless somebody tells you otherwise, then here's how we calculate it. It says not more than 10 times, 6 times the rated current of the primary or the second. In this case, it's most of them are on the primary. So you can go 6 times the full load current. Only for a transformer equipped with coordinated thermal overload protection by manufacturer. So your assumption is it doesn't exist unless you know it. They allow you to go higher here. Because why? You have protection from overload, guys. You have thermal protection, meaning you can't heat that boy. If you heat it, the thermal protection will open it. Some of these guys have sensors. Some bigger transformers have sensors in the gut of the transformer that goes interface with the relay, and the relay can trip the circuit breaker in case of an overload or temperature rise in the winding of a transformer. If you have a 20 meg transformer, you would hope that you protect that boy with everything that you can. You would hope that a fuse like this is not the only protection that you have for this 20 meg transformer. It's a huge piece of equipment, a huge investment. So what they do, guys, they put sensors, literally sensors, inside the winding of a transformer, wire these sensors into a relay, and then when you capture the signal as in a relay, then you can make a decision, either trip if it gets hot inside the transformer, or you can send an alarm to DJ, say, DJ, when you have a chance, your transformer is hot, getting hot, you know, go lower the load, do something. There's an action plan. So, but just keep this in mind. You assume doesn't exist unless you know otherwise. The assumption is. So you're going to be applying this rule unless you know otherwise. If you have primary protection only, tapping a transformer, you put the overcurrent protection device here, transformer, 10 foot, you have a panel. That's a primary protection only. Then they allow you guys to go 125 and all these multipliers, and here, no protection, of course, no protection on the secondary. But look at this is my main 125. Look how small the overcurrent protection device has to be if you're only having protection on the primary. versus 250. Everybody knows why, because if you have only one protection on the primary, meaning this does not exist. What if I have a short circuit here? A short circuit here, guys, it will take a long time for this fuse on the secondary side to see it. Why? Because there's a load here. There will be current going through the transformer here. So the short circuit here might not be high enough for this fuse to clear it, because the short circuit has to go to a transformer to transfer to the other side. So they want to limit that circuit breaker to a very small value, 125, so it trips fast. Any question about this? So when I ask you guys to go to 450.3b in the example I'm going to give right now, everybody knows how to go there and use it? Camille, my friend? Cool? Okay, so I'm going to go take a snapshot, close this, and let's minimize my code and go back to the example. And okay, my mouse. All right, here we go. Okay, so we have a snapshot. Let me put this one in a place where it doesn't interfere with my business. Oh no, Chad. We need it slightly lower here. How is DJ doing? Good. Good. That's good. Okay, let's take an example now. Everybody knows which table. Let's go right ahead and take example number 1. Example number 1. A beautiful transformer. A beautiful transformer, my friends. The rating of this transformer is 500 kVA. The primary of the transformer is 600 volt. The secondary of the transformer is 240 volt. I'm going to protect it with a primary fuse and a secondary fuse. Okay? My question for all of you is the following. It's my transformer. Number 1, I need to size the conductors. That's number 1. If I can write that number 1 here and stick it here. Oops. This is my beautiful transformer. All right. There you go. It's a 3-phase. Thank you. It's a 3-phase transformer, and I want to find number 1 is the feeder on the primary. Number 2, the overcome protection device on the primary. Number 3, the feeder on the secondary. Number 4, the overcome protection device on the secondary. Right? 4 things: fuses on the primary, secondary, and feeders or conductors on the primary, secondary, and then I'm done. Right? Okay, the first thing I want to do, guys, is number 1. Number 1, I need to find the primary feeder conductor size. Primary feeder conductor size. Primary feeder conductor size. The way you're going to find the I primary equal the 500K divided by 1.73 times, what's the voltage of the primary? 600 volt. I need to find the amps. When we size conductors and fuses, guys, you must know the amps. Otherwise, you're dead duck. Can't do anything. Anybody has a calculator handy? Cool. What's the amp on the primary? 482. I have another gentleman or lady? Yep, 482. 482 amps. Okay? That's the first thing you need to do. You need to find the primary current. Now here's my question for you guys. Is this the line current or the coil current? From now on, everything that we do is line to line. Line current, line to line voltage. The coil current and all this good stuff, forget it. That's the basics begin. Okay, great. Then from here, this is the full load current of a transformer. Now here's my question for you guys. I need to size a conductor that can carry this current. I need to size a conductor that can carry this current. Now, some of you are going to say continuous load, non-continuous load. We don't worry. When we account for the continuous load, guys, when we size the transformer. So when I came up with a 500 kVA, I took into consideration all my continuous load, all my non-continuous load adds up, and I decided my transformer is 500 kVA. So the continuous load is already encountered in this calculation. Okay, that's the assumption. All right, so I want to go directly and take my 482 amps. Where do you think I'm going to go? 310.16 cable, and under which column? 75-degree column. I bet you by the time you graduate from here, you're going to learn that one. How many conductors and why? Let me just give you a hint, guys. On the primary, most time on the primary I have a delta. On the secondary, I have a Y. Would that give you a hint? Most of these transformers, guys, most of them that we use them in the building, delta primary, secondary Y. Almost always, delta Y, almost always. But I have to tell you that because you need to tell me how many conductors I need. Excuse me. Okay, what's the then in this case, you're going to tell me 3 conductors, Chad, and what's the overcompression device for these boys? 800 kcm. We decided it would be a great idea to parallel here, but we decided not to parallel. So 3 conductors, 800 kcm each. 3 conductors, 800 kcm each. Not a good idea. We should have parallel, but hey. What would you do if you want to parallel? Divide this by 2, run 2 runs. Not a big deal. Okay, so that's a feeder conductors. Okay. The second thing that we need to, any questions? Bill, my friend, Camille, and Jem, and Urbab? No? Okay, so number 2, we need the overcurrent protection device for the primary. So that's called primary overcurrent protection device. Fancy name for a fuse or circuit breaker. In our case, it's a fuse. In my case, it's a Mr. Fuse. What's the multiplier and where do I go? So I take my full load amps 482, multiply this by what? What's the multiplier? It's more than 9 amps. Brad, what's the cable says? 250. Primary secondary protection, so 2.5. And I know somebody's going to ask me, where did you get the 2.5, Chad? This is coming from Article 450.3b. That's where the 250 is coming from, right? So nobody can ask me. That's called the preemptive strike. and what would you get?
1205.
How much?
1205.
1205 M. That's the option when you go to the bar. Be upset because you can't find a fuse. Or custom design at 1205. Or can I go up? Do I have the note that says go up there? Look at the note number 1. Do I have a note number 1? Note number 1? No? On 250.
Does not exceed the next higher standard.
No, you don't.
Do you have a note number 1 there though? Under that. It has to be note number 1 has to be note number 1, guys, have to be right next to the 250. Do you have the note number 1 right next to the 250? No, then I can't go up. Only if you have note. I know what the confusion is. You saw it under the table. No, that doesn't apply to everything in the table. It only applies for every percentage that has note number 1 right next to it. I don't have it, so what do? Go down. What's my down? How do I know what to go down or up, by the way? I'm going to go to 240, that's 6. And because I don't have my note, I have to go down. And what's the down? 1200? 1200. 1200 M. So my fuse would be at 1200 M. My fuse will be at 1200 M. M. Since we are Can I add one little thing, guys? Let's calculate the grounding conductor just in case we have the grounding conductor, just to get into the habit of calculating equivalent grounding conductor. So I'm going to add here that line here, and this one I'm going to call it, where are we at, 5? I'm just going to call it 5, and add one also here. I'm going to call this one number 6. Okay, well, this is the equipment grounding conductor. Can you guys add that one? Should have added it before, but 5 is the equipment grounding conductor. So I need to size the equipment grounding conductor.
3 out.
3 out. Let's go. Everybody got that one? Equipment. So I'm going to jump, instead of going to 3 and 4, I'm going to jump to 5 just to get the equipment grounding conductor. Then I'll go back. Everybody knows why I'm going to jump to 5? Just to finish the primary before I go to the secondary. So I'm going to go to 5. 5 says primary equipment grounding conductor. We take the 1200 amp, take it to table 250.11122. Why did I eat 1? 1, 2, and 2, and that will give me number. 2 gentlemen agree. A gentleman and lady. 3 out. 3 out. How many? 1. 1 conductor and a 3 out. 1 conductor, 3 out. Now we'll go back to a 3. Sorry for that. We jumped to 5 just to get the equipment ground conductor out of the way. Right? Equipment ground conductor. The assumption here, guys, with the equipment grounding conductor, here's the assumption. The assumption that the 200 amp, if it's close to the transformer, the overconduction device, there will be another 200 amp in the panel to protect the feeder. That's the assumption. But for all practical reasons, all what you need to do is just take the overconduction device from the primary, size it. 3 out. What was the feeder? The feeder was bigger than 3 out, obviously. Okay, let's go to the secondary. Secondary feeder conductor sizes. Okay, the first thing you need to know is find I secondary line, which is 500. Was it 500K divided by 1.73? And Holly, what's the voltage in the secondary? 240. And anybody have done the math for Chad? 1204. Thank you. 12O and a 4 amp. 1204 amp. 1204 amp. 1204 amp. That's a full load current of that transformer on the secondary side. Okay. Assumptions, continuous load, and all this good stuff is already taken in the transformer, so no need to multiply it by 1.25. Do you guys see what I'm hinting to? No need to multiply by 1.25. When we sized that 500 kVA, we took this into consideration. So, all right, so I want to take this one directly to 204 all the way to table 310.16. Which column? 75. I hope so anyway. And now I need to parallel. Now I need to parallel. Okay, let's parallel. Then I'm going to take, because it's too big, so let's just get the parallel first. I want to go around 3 runs. Anybody has problem with 3 runs? Oh, how about 4 runs? 4 runs, well, let's take 4 runs. I want to take 4. Mr. Erbab, I divided by 4 because I single-handedly decided to go 4. Why 4? Because if I divide by 4, I end up with 300 amps. I have a conductor that's in the 350, what is it, 400, 350 range, below 500. That's a good range of conductor to parallel. How would you know that? If you look at table 310-16, stay within around the 500, less than 500 kcm, 500 or less. Okay, what would that give you? 301 amp. Now we go to 310.16 under 75-degree column, and don't forget the word table here, and that will get me a healthy. Before I do the 350, I need to do the following. I need to go, how many sets? 4. Oops, let me use a different color so it doesn't get mingled with that. So I need a 4 sets. Why 4 sets? Chad said so. Of how many conductors? We're sizing now. We're only sizing at the time. It's a Y. So I need literally I need 4 conductors. But because the amp is so high, I'm sizing for this transformer. I'm going to size the 3 conductors first, and then I'll come to the neutral. Why? Because the amps are higher than 200. Okay, so 3 conductors. What size? Number 350 kc and amp. This is the size of my conductor. 4 sets of 350 kc amp. 3 conductors each. Why 3 conductors, 3 phase? Why 4 sets? Because we decided to parallel 4 sets. What does a 4 sets means? 4 conduits full of 3 conductors each. Well, it's going to be 4 conductors when we add the neutral. Okay, let's size the neutral because we split the neutral here, guys, because the amps are so high. So I'm going to go size my neutral. 1200. I'm going to say this size is phase sizes. If you guys want to add this one here, this is neutral size. Okay, neutral size. I'll take the 1200 again, 220.61. Okay, the first 200, leave them alone. Anything higher than 200 is what? 1004. What do you do with them? Multiply them by 0.7 and get me the answer, will you? That would be something like 700. No, not even close. So the first 200, leave him alone. Anything else? How much? 903. Any gentlemen disagree? Dare to disagree with my friend Spencer? No? 903 amps. 903 amps. 903 amps. Now, here's a question for you, my friends. Whom am I going to put the spot here? Should I put somebody on the spot? No. How many runs should I parallel now? And why? Do I have a choice here? If I'm paralleling the phases in 4, do I have a choice to parallel the neutral and then 3? So 3 conduits will have neutral, but the 4th one will, good luck. If you parallel the phases in 4, you're stuck with 4 for the neutral. Okay? See why now we have to parallel 4 because you need a neutral with every phase. Okay, so can I shift to the next one, guys? Would that here?
1004?
1004, yes.
Okay, cool.
Questions?
So then what you're gonna you're gonna downsize it then?
We're downsizing it.
It's a 903 in each one, or
903. We're gonna parallel 4 yet. We're gonna parallel them 4, divide by 4.
divided by 4 comes 220.
Yeah.
26.
So should I move?
Yep.
Okay. So we move to the second. We're still continuing to do 3, right? We're still sizing 3, and we're still doing neutral. Neutral. Okay. So what was it? The number that we came? The amps. No, the amps. 903. 903 amps. I have to parallel by 4 because I did the phases by 4. So that will give me, DJ, 226 amp, right? Everybody's cool with that? Then I take the 226 amps, take it all the way to 310.16, which column? 75-degree column. And what would that give me? And how many sets? 4 sets. Each one conductor. Each one of them is a 4-aught. A, W, and a G.
Why would you say all 4s?
Yeah. But the 4 sets of the neutral and the 4 sets of the phase, they're actually the same set. We put them in the same conduit. So we take one neutral and phase A, B, and C, one conduit, another neutral with the 3 phases, and the third neutral and the 4th neutral with the 3 phases. Okay, the last thing we when we do 3, 4, did we do 5, the overcome protection device, right? Let's size 5 secondary overcurrent protection device, fancy name for a fuse. Okay, what's the multiplier? 1.25. Multiply this by, what was it, 1204? What do you guys get? 1505 amp. Do we have a note number one? Note number one. Where did they get this number from? This is from table 450.3b.
Where's 5 from? You mean 4?
450.
We're looking for 4, not 5.
Oh, we're looking for 4. Did I? This is 4. Sorry. That's a 4. Secondary. That based on our label. 4. Okay. So do I have note number 1? Okay. Then I take this one to where? To 40.6, and I can go up because of note number 1. And what would that give you? 1600 amp. 1600 amp. 1600 amp. Now that's as high as you can get, guys. And I want you to do it for the test this way. For the test, I want you to do it this way. On the real life, you might have to say, you know what, I can go, do we have a 500 overcomputation device, 1500? 1200, I know we have. Do we? You might have to go, that's the maximum that you can go. Doesn't mean you have to go there. Does not mean you have to go all the way to 600. Do we have? We don't have 500, 1500. 1200 to 1600. So in a case like this, you might, and what was the amps of the conductor? The amps of the conductor? 1204. In a case like this, it might be a good option when you do the design to go down to 1200 to match the conductor's ampacity. But you can, by code, go all the way up to 1600. Most likely, you're going to probably drop it to 1200 or have an adjustable circuit breaker. What we do, guys, is we have an adjustable circuit breaker, and that you can adjust the circuit breaker to close to 1200 or maybe much lower than like 1500. I would adjust that circuit. If it's a fuse, it's not. If it's a circuit breaker, you can adjust that circuit breaker to 1500 because it's a big jump, 100 amp. For all practical calculation, that's what you're going to stick with, though. Any questions, guys? Any questions? The last thing, did we do a neutral? We did, when we do number 6 is what? The equipment ground conductor, right? We're going to do number 6, which is equipment grounding conductor. You take the 1600 amp all the way to 250.122. And what would that give me? One conductor? One conductor? Am I right with one conductor? Okay, 4-aught. Here's a 4-aught. AWG. How many conductors of equipment grounding conductors do I need with this feeder? One for every set. One for every set. So I need 4 conductors. 4 conductors. 4 conductors. 4 conductors, 1 with every set. 4 conductors, 1 with every set. Every time you parallel, guys, the equipment grounding conductor must run full size with every set of parallel conductor. In a case like this, is my set 1, set 2, set 3, set 4. I'm going to go 1, 1, 1, 1 here. And I'm going to go 2, 2, 2, 2 here. I'm going to go 3, 3, 3, and 3 here. What are these? The 3 phases, right? And I'm going to go to the neutral, or the grounding, 1 grounding, 1 grounding, 1 grounding, 1 grounding. I'm running out of color here. So which color do you guys want to add? Let's get the green again. Let's use the green again. And I'm going to have another green. Everybody knows why the other green is. Okay. This is how your conductors are going to be run. Does that make sense, guys? If I ask you, which I'm not going to do it here, go size me that PVC conduit schedule 80. Can you do it? What was the size of the conductors here that we did the phases? The phases were, huh? The phases were 350. The neutral was 4 and the grounding conductor 4 The grounding conductor was 4 almost as big as the neutral. And then can you find a conduit that fits all these? 350s, 2 4 Yes, no problem. Assuming you're pulling a full neutral, insulated neutral, and insulated ground. Any question, my friends? Any questions? So that's as ugly as it gets, as big of a transformer as you can get. As ugly as you can encounter. We did the tabs, we did the transformer. Just take a smaller size transformer, smaller numbers, and they will that will tab all the information about transformer. Okay, example number 2. I want to have a beautiful tiny little transformer. This transformer on the primary was a 480. On the secondary was a 208. The size of this transformer, 25 kVA, 25 kVA transformer, tiny little baby. And I decided to put a fuse here and a fuse here. And I want to find, don't forget the equivalent grounding conductor with it. And I want to find the following. I want to find number 1, number 2, number 3, number 4, number 5, number 6. I numbered them right this time.
The 3-phase.
Oh, it's a 3-phase boy. Oh, okay. What did you say? This is number 1. This is number 2. Okay. So I have a fuse. I need to size all this stuff.
2 is the wire.
2 is the wire. 3 is the ground. 3 is the ground. 1 is, thank you. 2 should be the fuse. 2 should be the fuse. Oops, losing my synchronization here. Okay. Let's erase this side here. Rearrange you guys a little bit.
It's 3-phase.
It's a 3-phase transformer, yeah. I don't want this color though. Okay. And I want, what did we say the fuse would be number 2? And the conductor is number 1, the fuse number 2, and the ground is number 3. Everybody got that one, guys? All right, let's go ahead and start. I'm going to start by primary. I'm not going to put the primary, guys. You guys know. You know what? Let's go for number 1. Primary conductors. I need to find IP IP equal 25K divided by 1.73. It's a three-phase transformer, multiplied by 480. Anybody has any? What's the amps on that? 30 even? 30 amp, that's good enough. I need the conductors. You take the 30 amp. You're going to go to 310, that's 16 under 60-degree column because you don't know otherwise. How many conductors and why? It's always a delta here and a Y on the second side. Three conductors number 10. Three conductors number 10. A, W, G. Okay. Number 2. Any question, guys? Straightforward. Just find the follow current, go to the table. 60 because 30 amp or less. Now, Brad, if they tell you a transformer is the logs most likely the transformer are 75, you can size based on 75 if you know that. Otherwise, 60 is good enough. Okay. Do I need neutral on the primary? No neutral on the primary. Don't split it too hard. The second one is overcurrent protection device. This was conductor. This was a conductor. Okay, overcurrent protection device. What's 30 times what's the primary? 2.5 equal 75 even amp. And then you take this one to 240.6 and what that will give you what? 75. If it wasn't a 75, where do you go? You go down. So 75. Do I need to do anything? It's 75. Multiply by 2.5 times 30, 75. I don't need to go down. Just stay 75. If it wasn't the standard, we dump it down. Equipment number 3.
Yeah.
Yes, sir.
75 isn't standard. It would be those 70.
It's not standard? Oh, you guys got me on that one. You're right.
Oh, you're right.
You lost your chicken with you. Okay, thanks. 70 amp. I got it. That sounded a little bit was 75. Okay, 70 amp. Right? We can't go up. There's no note for going up, so that's 70 amp.
Well, I mean, it comes to 69.47, eh? Oh, what is,
2.5
we're
times
doing
30.
2 secondary?
No.
Oh, I was doing secondary, so.
Okay. We're doing the primary, yeah?
Right.
Okay. Equipment, a grounding conductor. You take your 70 amp fuse to table 2, 50.1, 2, and 2. And that'll get your number, one conductor number. Number? 8. 8, thank you. Number 8. Okay. Now, here's the deal. If your conductors, look at the conductors on the primary, your overcurrent protection device is larger than the conductor size, guys. Larger than the conductor size. Your overcurrent protection device is larger than the conductor size. In a case like this, it doesn't have to be larger than the conductor size. Does not have to be larger than the conductor size. So I can use a 10. I can use it. It does not have to be larger than the conductor size. So what I can do, because of this, I can drop this and go one conductor number 10. One conductor number 10. Doesn't have to be larger than the conductor size. Okay. Any question, guys? Move there.
So that's equal to 10 now. You change.
Yeah, because the conductors are number 10 for the primary. You don't need the overcurrent protection device to be the equipment grounding conductor to be larger than the phase conductors. Okay, let's go to 4. Number 4. Number 4 is the primary, the secondary conductors. Conductors, secondary. Okay, you're going to find I secondary, piece of cake, equal 25. K divided by 1.73 times, what's the 208? What do you guys get? 70 amp. Okay, 70 amp. Take this one to 310.16 under 60-degree column. What do you get? How many conductors? 4 conductors, because they're small. Smaller than 800, 4, right? Smaller than 200, 4. How many? 4 number 4? For number 4, A, W, and a G. This is 4. Is that number 4? Yeah, that should be number 4. Number 5, secondary overcurrent protection device, which is a fuse. 1.25, right? Times, what's the secondary 70 amp? What do you get, Holly?
I'm gonna take it from 69 to
88. 70 equals 8 and 8 amp. Then you take this one to, not 310/16, Chad. You're going to take this one to 240.6. And what's, if it's not a standard, can I go up? Yep. Is it a standard? No. So where do I go? To 9 and a 0 amp. 90 amp. And the last thing is number 6. Equipment, grounding conductor, secondary. Are you guys following me when I say equipment, grounding conductor in the secondary side now? Where's the neutral here? The neutral is already included because they're small. Okay, you take the 90 amp, take it to table 250.1, 2, and 2, and that will get you number 8. Number 8. Do I need to up it or lower it? Look at that. No. We're good. We're not higher than the phases. We're good. Any question, guys? That's as ugly as it gets. Had these been a single phase transformer, what's the difference? You don't multiply by 1.73. It's the only difference. And the conductors become, if it's single phase, 120, 240. 2 conductors for the hot and 1 conductor for the neutral. 3 conductors. And plus the ground, of course. Same calculation. The number of conductors, still 3. On the secondary will be 3. On the primary, if it's single phase transformer, how do we have a single phase transformer from a primary side? On the secondary side, most likely it's going to be 240, 120. So you have 3 conductors. On the secondary side, what's a single phase transformer on the secondary side? You can either take it to 480. I can have a 480 transformer. I don't want to do the example. I just want to draw that. Here's my transformer. Ground this one. This is hot 1, neutral, hot 2. On this side, this is easy. This is most likely, it will be 240/120. How many conductors? Single phase. How many conductors? 3 wire or 3 conductor, right? 3 wire, 3 conductor. On the primary side, and you have your fuses here, all this good stuff. And this big fat thing is actually one big thing. On the primary side, how many conductors do I need? What voltage would be if this is a 3-phase system? Most likely, if it's in your building single phase, most likely it's going to be 480 volt. So this is phase A and this is phase B, right? That's an option. You get it just from one phase, tap it from one phase. That's what most likely you would do if you have a single phase transformer tapped from a three-phase system. But you would never do that. If you have a three-phase system in your building, if you have a three-phase service coming to your building, you run with three-phase everything. It will be less than intellectual to put a single-phase panel when you have a three-phase system. Always run with three-phase system everything. So, but if this is your transformer, if the voltage is 480, it could be 480. If your voltage is doubt that they will be, so if your voltage say 208, it could be 208 volt. The same thing, guys. Between two phases, phase A or B. Does it have to be A and B? Can it be B and C? No problem. Any two phases. You know, because the transformer, the system that I'm having here is right in here. I'm just tabbing any of these two phases. Here's my phase A, phase B, and phase C. That's that's a system. And I'm tabbing from any of these two phases. The other one, it could be also 600 volt. And the last one, if it's a utility transformer, F utility transformer, you're going to find 7200 volt, which will be between phase, this will be phase A and neutral, or you can have it 2400 volt. Also could be between phase A and B, or you could have a 13.8 thousand volt, and that would be between phase A and phase B. So multiple voltages, most commonly used, guys, 7200 volt in the if it's utility side, which we don't size, we don't care too much about it. But we could have these systems in our building, and we size based on the high voltage. We will go there when we do the industrial. Besides the transformer, if the voltage here is 13.8, how do you size the cables for 13.8? They're not 600 volt. We can't go to the same table now, can we? No. Any question, guys? That will wrap up chapter 6, basically. Hopefully that will be clarify a few things for you. Almost lunchtime? Almost. Okay, that's all I have. Thank you, guys.